Right, let's take a look at an example to illustrate how do we solve problems, permutation problems with some restrictions. Right, let us take a look at this example. There are four parts to this example. The first part is when part A is the easy one where there are absolutely no restrictions such for how can we arrange 3 men and 3 women in 6 seats. Right, 6, this is 3, this is 3. So quite easily, right, when how many ways can it be done? No restriction, this is an example, no restriction, just 6 factorial because there are 6 slots and you want to reach 6 people. Clear and simple, done. Now part B, let's take a look at part B. You want no 2 women and no 2 men, no 2 men and no 2 women sit together. This is part B of the example. No 2 men and no 2 women may sit together. Usually when we deal with problems with restrictions, we try and we try and draw it out and be as concrete as possible. Okay, so you think about it, we have to alternate the man and woman. There's no other way to do it. It's either man woman, man woman, man woman, or woman man, woman man, woman man. So there are 2 different ways of doing it. So let's count number of ways for each case. So still at B, let's count. So if there are 3 slots, man, woman, man, woman, man, woman, for the 3 men there are how many ways can we arrange the 3 men? It must be 3 factorial ways. We've learned it earlier. 3 times 2 times 1. 3 ways here, 3 ways, 2 ways here, and 1 way here. Now, similarly for the 3 slots for the woman, it must also be 3 factorial ways to arrange the woman. So, quite clearly, to have man, woman like that, this is man, woman, man, woman, man, woman like that, it must be 3 factorial ways. But surely the other woman, man, woman, man, woman, man way is also similarly 3 factorial ways. So therefore it's 3 factorial plus 3 factorial. This plus because it is you use the addition principle because these 2 cases are mutually exclusive. Now I'm not going to write it down, but there's an alternative method of solving it. You could actually say 3 factorial times 2 because you could first say it could be 2 different ways, but the 2 different ways are exactly the same to arrange it could be man, woman, man, woman, woman, man, woman, man. They're exactly the same. You could times 2 as well, but the concept is similar. Let's look at part C. Again, a different kind of restriction. Now you have a specific woman called May, April, and June, and you want them to be seated together. Now, this is the first instance you see such an example where you have a restriction, and restriction is 2 things must be bundled and grouped together. The trick to doing this kind of problem is to group them together like this. If you get A and J, you group them as a unit like that. If you can take a look here, you group them as a unit. So whenever you move them, right, you group them as a unit, and then after that you permute, you arrange, not as individual A and J, April and June, but you group them as a unit. So how do we arrange them? This you see like that. The A and J move it together. So instead of 6 people arrangement, you move that as a unit. There are actually only, if you count here, 1, 2, 3, 4, 5. There are actually only 5 units. Right? There are only 5 units. So the total number of ways must be 5 factorial because there are only 5 units. Because A and J are grouped together as 1 unit here. But the A and the J can be arranged. So you multiply by 2 factorial because it can be AJ and JA. So you multiply by 2 factorial. You multiply because it is done in succession. Correct? These 2 operations are done in succession. You arrange 5 units first. Then after that you multiply by 2 because you arrange the A and the J. So therefore final answer is 240. Final one. Final part D. April and June must not be adjacent to each other. That means they are not together basically. They are not together. So if you see part C is the number of ways that April and June are together next to each other. So you must think of it as they are adjacent and they are not adjacent. These 2 events are known as complementary events. Complementary means it is either this or the other. There are no in-betweens, and these two added together, the number of ways that these two added together must be the total number of ways. So the number of ways that they are not adjacent to each other must be the total number of ways that you can arrange. This is essentially without restriction, which in your part A answer was 720, minus this is your part C answer, this is part A answer basically, where the number of ways that they are together. That they're together. Right? So it must be 720 minus 240, therefore answer is 480. So through this example, we learned this key idea of complementary events. Right? Complementary events, when they are mutually exclusive, yes, like what we said just now, the earlier example, whether adjacent or not adjacent, either next to each other or they are separated, they are only complementary if their union covers all possible outcomes. So this is a key idea in this example.